This video might be a little lengthy, but I wanted to cover it all at one time because the two things are so related. So we're going to talk about both exponents and radicals. First is, what is exponential notation? So the idea is here, if I have some base to a power, right, 2 to the 4th, what that means is I have 4 2's multiplied together, right? Some very common properties here if I have 0 or negative exponents. So if I had any number at all, so I'll just call it a, because it could be any number at all, to the 0 power, anything at all to the 0 power is 1. And then negative exponents, if I had a number to a negative exponent, so a to the negative n, what happens here is it goes to the bottom, right? I put a 1 on top, it goes to the bottom, and I have a positive exponent there. If you have a negative on the bottom, so for example, if I had 1 over a to the negative n, then that can simply come back to the numerator and become a positive n. Okay, so 0 exponent, whatever the base is, doesn't matter, it becomes 1. If I have a negative exponent, you move it from where it's at, so if it's in the numerator, put it in the denominator and make it a positive exponent. Some laws of exponents. You should have learned all these in Algebra 1 at some point in time. So if you have the same base, if you are multiplying those things of the same base, you can simply add the exponents. So if I had 2 to the 3rd times 2 to the 4th, that becomes 2 to the 7th. I add the exponents there. Which should make sense because you basically have 3 2's multiplied together and then 4 2's multiplied together. And if I multiply all that together, then I really have 7 2's multiplied together. If you are dividing the same base, you subtract the exponents. So if I did 2 to the 4th divided by 2 to the 3rd, that's just going to give me 2 to the 1st. I subtract 4 minus 3. If I have a power, this is called a power to a power. So if I had 2 to the 3rd and then I raise that to the 4th, that is when you multiply the exponents. So that would be 2 to the 12th. And again, if you really think about that, that should make sense. I have 3 2's multiplied together here, and then I have 4 of those things all multiplied together, right? So I've got 2 to the 3rd 4 times, which is why I end up with 2 to the 12th. If I have a product to a power, I can simply just distribute that power to both of them. So if I had like 2 times 3 to the 4th power, that's going to give me 2 to the 4th times 3 to the 4th. And just distribute that power there. The next one's basically the same thing. If I have a quotient to a power, I can distribute that power to both things in the quotient, which is what you see here. I'm not going to do an example of that one. This next one's kind of important. If I have a negative exponent on a quotient, so if I did 2 over 3, and I took that to the negative 4th power, that's the same as just flip the inside here, 3 over 2, and now I can make that a positive 4th power. Okay, so if you have a negative exponent, just simply flip the fraction on the inside and make your exponent positive. And then the last one is kind of what I was talking, the same thing as that, or kind of what I was talking about up here, where if you have a negative exponent, you simply move that, if it's in the numerator, to the denominator, and you can make it a positive exponent, or you move that whole thing to the numerator if it's in the denominator, and make it a positive exponent. Okay, so I'll go ahead and move on. But those are the exponent properties you should have learned in Algebra 1 a long time ago. Just a refresher on those. Okay, radicals. So radicals, you consider these probably square roots. A square root is just simply the most common of all radicals that we use, so don't just necessarily say square root all the time, because you might have a cube root or a 4th root or something like that. So all of these properties apply, whether it's a square root or anything different, for all radicals. The first one says if I'm going to do a root, so I'm just going to do a square root. If I'm going to do a root of a product, so think about this as maybe, I don't know, the square root of 8. And I want to think of 8 as 4 times 2. What this is saying is I could break that down into the square root of 4 times 2, which then could be the square root of 4 times the square root of 2. I can split that up into the product of those square roots. Same thing with a fraction. I could do the square root of 9 over 16, and that would become the square root of 9 over the square root of 16. Okay, I can split that up into separate square roots there. The next one is if I have a root inside of a root. So let's say I did the cube root of the square root of 10. This becomes, by the way, square roots, if you did not know this, square root has an understood 2 there. So make sure you know that. But if I do the cube root of the square root of 10, what this is saying is I could just multiply these two roots together. 3 times 2 is 6. I could really just do the 6th root of 10. And then this is basically saying that radicals and exponents cancel each other out, kind of. We just have to be a little bit careful. So if n is an odd number here, so let's do the cube root. So if I did the cube root of 2 to the 3rd power, this is saying I just get 2 because that root is an odd number. Okay, so if that's odd, those will cancel each other out, and I just get whatever that number is. So if it's negative 2, I get negative 2. Okay, it works the same way for both positives and negatives. However, if n is even, so if I were to do the square root of 4 squared, I have to be careful here. I get the absolute value of that number inside there, which is going to give me 4. Okay, so some people think, hey, if there's a negative inside there, that doesn't work because I can't do the square root of a negative. Well, because that 2 is on the inside, what this is saying is I would get the absolute value of that instead. I would get positive 4 instead of just being negative 4. So a lot of people think that the square root and the exponent, the square, will cancel each other out. That's not necessarily true if that root is even. Okay, you get the absolute value of whatever that number is. Okay, combining radicals. If I were to want to add 2 radicals together, so I won't necessarily talk about the multiplication of them because that's covered in this exponent or this radical property up here, kind of backwards. If I were to multiply 2 radicals together, I can simply just bring them to a single radical and multiply those numbers on the inside. So I can do that. But if I wanted to add them together, so let's say I wanted to add the square root of, let's do the square root of 20 plus, let's do the square root of 45. No, that's not good. Yeah, that'll work. Okay. Square root of 20 plus the square root of 45. I can't just say the square root of 65. That is not true. Do not do that. Some people will try to do that. That is not how you do that. What you have to do is break these down. And you have probably done this before, whether you made a factor tree or you looked for a perfect square that was a factor of this. You've done something to try to break that down so that you can simplify it a little bit, right? So what I mean by that is that there's kind of 2 schools of thoughts. One would be, all right, I have 20. I can break this down into, say, 2 and 10. I break that down into 2 and 5. So because I have a pair of 2's, I could rewrite this as 2 times the square root of 5 and leave that 5 inside there because there's only one of them. That's one way you can break down a radical. Another is to just think of the number and say, well, I know that there is a perfect square that's a factor of that, right? I know that 20 is 4 times 5, and 4 is a perfect square, so I can think of this as the square root of 4 times the square root of 5, and the square root of 4 becomes that 2 on the outside. So whichever one of those ways makes sense, stick with it. Either look for perfect squares that are factors of that number, or just make the factor tree if you cannot figure it out that way. So the square root of 45, I'm going to take this second school of thought here. I know that 45 is 9 times 5, so I can think of this as the square root of 9 times the square root of 5, which means I get 3 times the square root of 5. And now, because I have this square root part the same, now I can add these together. And what I do is I basically think of that square root of 5 as like a variable. I have 2 root 5s and 3 root 5s, which means altogether I have 5 square root of 5. Not the same thing as the square root of 65. If you don't believe me, plug into a calculator. It's not the same thing. Okay, so in order to add or subtract radicals, you absolutely have to have what are called common radicals. So what that means is the number on the inside has to be the same, and whatever the root is has to be the same. So they're both square roots in that case. If one was a cube root, I couldn't do it. They would both have to be cube roots. Okay, so they need to be the same in order for that to happen. Okay, next up is rational exponents. So if you have some base to an exponent that is a fraction, a to the m over n power, the way that you can think about this is you have a to the mth power, and then you're going to do the nth root of that. Or if you want to do it I guess opposite in terms of the order of those, you could do the nth root of a and then take that whole thing to the mth power. You will get the same answer either way. And I'll explain to you why one may be better than the other, but in most cases. Let me give you an example of that. If I wanted to do, let's say, 8 to the 2/3 power. Okay. And again, how do I remember which one goes inside as the exponent? How do I know which one is the radical? Think of it as power over root, and roots, like tree roots, are on the bottom, so I know that my root is going to be the 3, and my power is going to be the 2. Now, I would suggest you do the root first. If you do the root first, you're going to deal with smaller numbers, right? So the cube root of 8, what multiplied by itself 3 times is going to give us 8. That's going to be 2. And then I need to square that, and that's going to give me 4. If I wanted to, I could do the power first. So I could do 8 to the 2nd power, and then do the cube root of that. I'm going to get the same thing. So that would be the cube root of 64, which would also be 4. Okay. My suggestion, again, is if I'm dealing with rational exponents, I like to take care of the root first. Because if I do that, I would much rather do 2 to the 2nd power than the cube root of 64, right? I'm going to be dealing with smaller numbers, and I should be able to do that in my head a little bit better if I do that first. Okay. All right. Converting between radicals and rational exponents, I kind of just covered that with this rational exponent idea. Sometimes you're going to want to use that, and it'll be helpful to do some operations, which I'll show you in just a second. But consider this to be kind of the same thing as what goes underneath here. So simplifying radicals as rational exponents. So if I wanted to do the square root of 2 times the cube root of 2. I could use exponent properties to do this. I could use radical properties. I just want to show you what this kind of means is if I were to switch this around. Or actually, let me do this. Let me make this the square root of 2 cubed. Okay, so as soon as I get that base to kind of be the same thing, so let's say that 2 cubed starts as an 8, and then I rewrote the 8 as 2 to the third. What I would want to do here is rewrite these as rational exponents. And it's going to make it a little bit easier to deal with because I know exponent properties. Okay, so this first one I've got 2 to the third, and I'm doing the square root of that. So that becomes 2 to the 3/2 power times, this one would be 2, well my power is 1, and my radical is 3. So I've got 2 to the 3/2 times 2 to the 1/3. Well, now that I have the same base, you should know from exponent properties that I could then take the exponents and add them together. 2 to the 3/2 plus 1/3 all inside my exponent. Okay, well then how do I add 3/2 and 1/3? I need to get a common denominator, which would be 6. So I'm going to multiply that by 3. So it's going to be 9 over 6 plus 2 over 6. Which is then going to give me 2 to the 11/6 power, which if I want to then go back to radicals, I've got the 6th root of 2 to the 11th power. So that's supposed to be an 11. 2 to the 11th power, right? It's a little more challenging to do and sometimes to think about as radicals. So you want to know how you can switch things to rational exponents to maybe make the work a little bit easier for you. Okay, so that's that idea. The last thing here is rationalizing the denominator. I'm sure that this is something that you've heard about before. The idea is you do not want to have a radical in your denominator. It's just not the simplified way to write that. So if I had 1 over the square root of, doesn't really matter what the number is, 2, I don't want that, right? So what I have to do is I have to rationalize the denominator by multiplying both the top and the bottom by the square root of 2 in order to get that to happen. On top I would get the square root of 2, and on bottom I would get either think of it as the square root of 4, or just know that when you multiply 2 square roots with the number on the inside being the same, you just get that number. Right? So square root of 2 over 2 would be my final answer there. And I no longer have a radical on the bottom, which is what I want. Now, you don't necessarily always have to go. Sometimes you don't have to go with as big of a number as what you can maybe avoid that. So let me do 1 over the square root of 12. Okay, I don't have to multiply by the square root of 12 on top and bottom. I can, but I want to think about what's the smallest thing I could multiply that by in order to make the bottom be a perfect square. That's kind of the idea. And so if you think about 12, 12 is 4 times 3. And the 4 is 2 times 2. So that part's already a perfect square. All I really need is another 3. Right? If I get another 3 in there, then I'm going to have the whole thing being a perfect square. So instead of multiplying by the square root of 12, I'm going to multiply by the square root of 3. And that's going to give me the square root of 3 over the square root of 36. Which would give me 6 on bottom, right? The square root of 3 over 6. And what you have there is a reduced answer. Again, I said it wasn't wrong to multiply by the square root of 12. You could do that. 1 over the square root of 12. If I multiply by the square root of 12 on top and bottom, I get the square root of 12 over 12. This is the same as that. It may not look like it, but if you simplified that square root of 12 on top and then you reduced, you would get the square root of 3 over 6. So my suggestion is don't always just multiply by whatever's on the bottom. Think about what's the smallest thing that you could use to make that thing on the bottom be a perfect square so that then the square root's going to go away. Okay, so a lot of stuff in this, but again, it's all so related. The exponent properties, the radical properties, and then using those to maybe help you do some different things. So thanks for hanging in there. I know this is a bit of a long video, but again, all of that is really related, and I wanted that to all be in one place for you.